The last two questions are more conceptually demanding. So try to pause the video, do it first, we'll go through this together. Okay, so first of all, in terms of the question, what we can find out from the question is we know the mass, we know the angle, there's an inclined plane. There's no friction, so you don't have to care about the work done at all. It's basically the conversion between GPE, because you know there's a certain height that you start with, and it is from the rest. So that means that there was no KE, and later on, the whatever GPE is lost, that would convert into KE, so should be quite simple. But for part A and B, they ask you to sketch the graph for kinetic and potential energy in terms of time and also distance separately. So some of you may simply just like maybe draw a graph like energy and then time, and then you just randomly draw something. Say maybe you think that kinetic energy is 0, and later on is a certain high value, so you find maybe they're just 2 points and you just connect to it, so like this, and you think this is KE, and then GPE will be probably the opposite, because you should know the sum should be a constant, something like that. But the thing is, you can't just blindly guess when the context is given like this. So what I mean is, who knows this is a straight line? It could be a curve like this. It could be a curve like this, right? I mean, it can be anything. So instead of just stating the relationship as in, when time increase, KE increase, how exactly, and also mathematically, how the line should be, like what kind of mathematical model it should follow, will be very important, and therefore you should write down some equation before you draw the diagram. Okay, so let's think about these first. Okay, so here's a way to do it. First of all, the question set, it wants you to relate the kinetic energy and potential energy with respect to time. So just do one of them. I would say just do kinetic first, and then you can guess potential, cause you know when they add together it will be constant, so it will be like you just minus a constant value, you can find potential if you find kinetic. So the first thing that you want to recall is the KE equation here, half mv square, and your task is whenever they ask you to do this, then you are going to relate the KE, the whole thing, with respect to time. So eventually the whole equation here, you can see at the end there will be a t over there. Alright, doesn't matter whether it is a square root, whatever, inverse, doesn't really matter, exponential doesn't really matter, you must have t in it, and also the rest hopefully will be a constant, and that will be the best way to relate them. So in this case, how you can do it is, you can see here I changed the v into u plus at, because that's what you learned from kinematics equation. And once again, I would like to remind you and encourage you to memorize the equation that you learned in physics. So even though IB Physics give you the data booklet, so you can always refer to the formula, if you want to be a good physicist or physics student at least, you should memorize the equation, and in this case you'll be more sensitive to this kind of situation where you have to kind of substitute something and change the equation. Just like when you talk about Pythagoras theorem, if you can't remember that even, then you won't be good at geometry at all. So say here, since u was 0, because again the question said it was at rest, and so you just have to deal with a and t. And for acceleration, if you remember from mechanics, like in the Newton's second law we learned, the only force that is dragging it down, because there's no other thing like friction, will be the weight component. So once again, that's the thing that I asked you to memorize, and for the force that is going along the slope downward would be mg sine theta. Alright, so in this case it will be mg sine 30 degree times the t will be the one that you want to keep here. If you just expand it, then what you can find at the end is you will find m squared times g times sine 30 degree divided by 2, and this whole thing is actually a constant throughout the whole motion, so you don't actually have to care about them by this point. Of course, if you want to calculate, you can calculate this, and that will be like the coefficient. But the most important thing here is you find out that Ke is proportional to t squared. Or you can write Ke equals to Kt squared. So if you don't know how to plot this, you can go to use your graphical calculator, or you just revise your maths, or you can go online to find a website like this one. And so you can kind of see how it looks like. So basically it's a curve that would increase with an increasing slope like this. Okay, so that is how you should be drawing here. So that will be the Ke. And once again, for the potential energy, since you know when they add together, when both Ke and Pe add together, it should be the same constant throughout, then you can kind of see that the potential energy is just the inverse of it. So initially will be less steep, and so it should hit around the half when they intersect. So I can draw a little bit better, like so. And so that could be the potential energy. So this would be the graph for energy against the time. And of course, if you really want to find the expression for potential energy, you can also do the similar thing here. Start with Pe equal to mgh, and probably you change the h with respect to the so-called distance moving along this. You should be able to do that easily. Alright, so for the part B, asking you to relate the energies, the two energies with respect to distance, if you understand what I did in part A, then you should know what we should do in part B. So it will be starting with Ke definition again, half mv squared, and you want to change the v in terms, because m is constant, right? You can't do anything with it. V is something you can change the expression into something related to distance, and that could be u squared plus 2as, right? Because that is one of the kinematics equation, and u again was 0. You just take it away, and then a, like what we said, it will be mg sine theta, and then s will just keep it here. So at the end, like similar to part A, you will have a constant or a coefficient, as in m squared g sine 30 degree, which is unchanged throughout the whole motion, times the distance. So here you may be wondering, should we talk about the vertical displacement, or should we talk about like along the plane? All right, so which one should we take? If you look at the question, what they said, they have specified. All right, sometimes the textbook is not telling very clearly, but then this one is quite clear, that is traveling along the inclined plane. So that is the slanted direction here. All right, how much you travel. But then this actually is exactly what we want, because ultimately when you talk about V, or when you talk about A, these are always going in this direction also. So S is just all right. The other thing is, even if you are trying to find the vertical displacement, then you can just imagine you're taking a component out of it. So you may be just multiplying a trigonometry like sine or cosine to it, and that has nothing to do to change the shape of the function. So you may just be multiplying one more thing here, but then ultimately the equation is still be Ke, which is the y in your equation, y equal to Kx simply. So when you try to draw the diagram, I mean the graph for this, you will have Ke just increase linearly, and so like we said, since the sum of the two energy, when they add up together, it will be a constant. So for Pe, it would simply be the other way around. Oops, I can draw better. All right, and so they should intersect around the half. I suppose will be the half point. Cause yeah, that must be the half point. So then that would be the E against distance s, right? If you want to find the exact value, of course you can do it also. And lastly, for part C, I think now it's just trivial. I mean, it's always trivial because you should know at the beginning when you try to do this question. So that's all for this question. Alright, so next question. This is a diagram that I can understand from the question. So you have an inclined plane with angle theta. There's a block, and you just got pull up with a tangent t. I guess there's a typo in the question that there shouldn't be a word is here. Just say find the tension in the rope. And it wasn't well declared or specified that whether this is a frictionless or a plane with friction. So I think I will assume it is frictionless. Alright, otherwise I think we can't do it in this case. So we assume it's frictionless. So in this case, then obviously the tension would just be balanced because you have constant V, right? That's just like what you learned in the previous chapter. That since A is 0, because V is constant, and therefore the net force is 0. And so the only force that is countering tension is again the component of weight going down the slope, which is mg sine theta. This is not a best way to draw free body diagram. I mean, it is not even free body diagram, but I hope you understand it. So the tension would just be mg sine theta. Alright, and you don't know any exact value, so just leave it this way for part A. Part B. So it said calculates the work done by the tension when it's moving up with the distance d meter along the plane. So it's actually quite easy because you know the work done is simply, I always write this one, W equals to F times D. Cosine theta you may say, but then here you can see the tension and the distance that you moved, say that's D, is parallel. They are parallel, so you don't have to take any angle. So it would simply be the tension times D, which I guess you can express using the answers from part A. So mg sine theta times D would be the answer for part B, I suppose. And if you look at part C, it asks you to calculate the work done. Again, I don't know why there's an extra word. Find the work done by the weight of the mass. So once again, it will be using this equation for work done, F times D. You can see that the force, again, is parallel to the distance you move D here. And so you don't have to do much. You don't have to take the cosine. You just have to substitute everything in, but then they are in opposite directions. So you may claim that it is negative mg sine theta times D, and obviously this is the negative of the answer from part B, or the other way around. And that makes sense because throughout the whole motion you don't actually gain any kinetic energy, so these two basically will just cancel out each other. So the work done by the tension basically cancelling out the weight component going down the slope, and that's why velocity is constant. As for part D, it asks you to calculate the work done by the normal reaction force on the mass. So normal force is pointing this direction, or reaction force pointing in this direction. And once again, W equals to Fd, but then this time you can see it is 90 degrees between the distance and the direction of this normal force. So you can say, oh, it is cosine 90 degree, having the angle between them is 90, and if you recall, cosine 90 is simply 0. So the work done will simply be 0, no matter how big the normal force or the D would be. So it's a conceptual question actually, there's nothing to do with calculation. So at the end, part E is asking you what is the net work done on the mass. So obviously, including like all the forces, because there's only 3 forces, right? So that's why I do think there's no friction, because they didn't ask you about friction. The only 3 forces that we did is tangent, mg sine theta, and normal force. You may actually claim that there is actually one more, that is this direction, same magnitude to the normal fault, which is mg cosine theta. So if you try to calculate the work done of this, it will also be 0 anyway. So at the end, since these two, the answer from part B and C cancel out, so the net work done will be 0 simply.